kind of a crazy week. Okay. So Alex reports. All right. I definitely want to set up a blinking light for next Wednesday's homework. Okay. Mondays, we're going to cover everything for Monday today. So I'll be talking about Wednesdays on Monday, but definitely get done with Monday as soon as possible so that you can start working on Wednesday. There's a lot of little things on Wednesday that are easy points, but if you wait till Tuesday or even Wednesday, which would be even worse, you may run out of time, and it's a bunch of easy points. So don't screw this one up. Get done with Monday as fast as possible. Do that today, and then start on Wednesday because it's pretty easy. It's just learning about electron orbitals, and stuff like that, quantum numbers and things like that. So it's a real simple set of questions. There's no calculations really. The calculations are more for Monday. So for Wednesdays, it's just learning about atomic orbitals and quantum numbers. And so we're going to talk about that on Monday, but I would say jump on it as soon as you can. So we're pretty well done with stoichiometry. Can you give a cheer? Yay! All right. So we've done all of the different, I know, she's like, I love it. That's okay. So now we're going to change gears a little bit. We're going to talk about light and spectroscopy. And so this spectroscopy is the interaction of light and matter. And it's the tool we use to, what I say, see the unseeable, right? You say, well, can you see an atom? Not really, but the evidence that we have that atoms exist comes from spectroscopy. So we're going to learn about how we use spectroscopy today and how to interconvert the wavelength of light to the frequency of light and all of that stuff. So we're going to learn all about light today and spectroscopy as a tool. It's how we determine the behavior of the electron cloud and the nuclei and the molecules. It's also how we learn about our universe. So we can, when I was a kid, and all I thought astronomy was just looking at, through a telescope to kind of see where the stars were. Maybe you see the rings of Saturn, maybe you see some moons on Jupiter. It was cool, but now they put spectrometers, the little Cheez-It spectrometer thing, on a telescope, and you can actually see the chemical composition of the stars without even going there. So you can determine how much iron is in a star that's a billion years away, and you've never even had to go there. So that's how we're using light and spectroscopy to understand how old a star is 13 billion years ago. So that's pretty cool. Okay, also the chemistry of health and disease in your body. So magnetic resonance imaging or positron emission tomography, all of these diagnostics that we use for our bodies. We can look at, my father just went through heart surgery, and my father-in-law, and they determined that his heart was blocked without invasive surgery. They did a CT scan and looked at the flow of the blood through his vessels, and they didn't have to open him up to determine that. Why? Because of light, because of X-rays. So this is how we see the unseeable. So there's some terms in here. We talk about absorption and emission. And Alex is using these terms, but I wanted to kind of give you the theory behind some of these problems in Alex. So this is how we measure an absorption spectrum. We have a source over here, white light. We split it apart. In that Cheez-It spectrometer, or in those glasses, those use a diffraction grating. And so it could be a prism, or it could be a diffraction grating, which could be just like a film. So let me try to draw it here. A film with a bunch of scratches on it. Just like a grate on the sidewalk, you walk across, it's a metal thing with a bunch of lines on it, the same kind of thing, only it's on that plastic is a piece of plastic with lines that are scratched on it, and that's enough to cause light to interfere with it and split apart. And so we just need some way of splitting light apart to where one wavelength goes down and the other wavelength goes up, and we can get this separation of wavelengths. So what we get up over here is what's called a spectrum. Okay. Now we could put we could take a spectrum of the source, and then we could put something that absorbs light in the beam. So we put something that absorbs, and some of those wavelengths are going to be missing. Okay, so it's taking away certain wavelengths of light. We call that absorption. It's absorbing that light. And then we get a computer to look at the detector, and then we plot that. So these peaks on here are the spectrum of our substance, and this would be the absorption peaks. You see where the black lines hit the x-axis. We got the wavelength there. So this is an absorbance spectrum. Normally we would look at it 90 degrees to this, but this is what we would see. Now, in the old days, they used a photographic plate, okay? And they put a slit, like a horizontal slit on the source. So that CHEM spectrometer, notice how when you look through it, you saw these horizontal lines. If you took your eye out and put a camera there, you get a photographic image, and those spectral lines would be what we call lines. So in this terminology for spectroscopy, you look at that, you say, well, that's a peak. Yes, you would call it a peak. But the terminology of the old days, when they used photography, they called them lines. Just like that CHEM spectrometer, you see those lines? So these peaks are also spectral lines. So that word line is where a peak is in the spectrum, spectral lines. Okay, so that's an absorption spectrum. That's measuring the missing light. So you get a peak wherever the light was absorbed. Now we could also measure an emission spectrum. So we could take something that emits light, like a star, way far away, or these tube lights in the room, and run them through our diffraction lens and straight to the detector, and we would see the light that comes out of the source. So we've got this light that's coming out of our match, hits our dispersing element. It could be a prism, it could be a diffraction grating, and then that starts to split apart the wavelengths of light. Okay, and so in this case, I'm showing that it's given off two major colors, kind of a red and a yellow, and then wherever that hits our detector, we get a peak or a spectral line, and we call it emission. So those are emission lines. Notice the light, the background is black, and the light is emitted, and we have a peak wherever there's an emission line. That's what we see in the spectrometer, the CHEM spectrometer. When you look at the tube lights, you see no light, and then you see bright lights where the mercury is emitting. So the mercury is giving off 5 major peaks: red, green, blue, a little bit of yellow, and some red. Okay.
So emission is the colors that you see, and then absorption is the colors you don't see.
Right. Absorption is the missing colors. So we need to take 2 spectra for absorption. We have a background and a sample. We compare those, and where the light's missing, we draw the peak. So the computer does all that for us. I don't know if I could get the video to see this. Let's try it. I'm going to screw something up, I'm sure. Let's see. Yeah, there it is. You see those spectral lines? If you're watching on the video, you see the 5 colors: red, green, blue, yellow, and so on. Okay. Yeah. All right, so that's pretty neat. So here we can now tell the difference between different substances, so atomic substances, based upon their emission spectrum. Isn't that cool? So this is strontium here, and very different than calcium, very different than barium. You see, look at that: strontium, calcium, barium. Very similar elements, very different spectra. Strontium has a lot of green, a big red one, but calcium has a really bright green line and a really bright red line. So look at xenon. Xenon has a crazy number of lines because look how big it is. So those electrons are way far away from the nucleus. There's lots of transitions that it can have. Look how easy, how limited hydrogen is. So hydrogen is right here. It's got a really deep blue line, a bright blue line here, and a red line there. Super simple spectrum. Okay. And then looking through those fireworks glasses, this is a video I took through those glasses. So that's why you want to get those for 4th of July or New Year's. that cool? Yeah. So definitely recommend. Yeah, 10 out of 10. All right. Anyway, that's the fireworks. And if you were to capture a spectrum, so here I've got the white light from the fireworks. I kind of grabbed one of those little rainbows here. You can kind of see a bright dot in the green. You see that bright dot? It's a little brighter than than the left and right. Okay, and so that little bright dot, it could be lithium. I mean, maybe it's calcium. Maybe it's krypton. I don't know. Probably not a noble gas in a firework, but they could put in a lithium salt or a calcium salt. Calcium's pretty common, pretty cheap, so it might be calcium. So whatever that burning paper, it has gunpowder and paper. All you got to do is soak that paper in a salty solution. So calcium chloride. You soak that paper in calcium chloride, pack it full of black powder, put a charge to get it up there, a little fuse that makes it blow up when it gets up to altitude, and then whatever salt you put in there, it's going to give off this emission spectrum. Now you know.
I want to make fireworks.
Yeah. Don't do this at home. It is cool though, but that's how it's done. Okay. Now maybe it's not just soaking the paper. Maybe they actually put a lot of salt in there. I don't exactly know the details, but you just got to get those elements hot, and then this is the emission spectrum that they spit out. Okay. Look at this one. This one is bright red. You got a couple of dots there. Okay. But no yellow, no green, no blue. So that right there is a pretty interesting signal. And again, if you could figure out what the nanometers were, in that dispersion from that fireworks glasses, you could find those dots, and then you could go look at a database of all the elements, and you could identify what salt that was. Okay, so that's pretty cool. It's not just, but that has forensics applications, right? And so this is what we do in the lab. We'll take a nebulizer for groundwater or whatever. We'll run this water and all the elements through this really hot flame and look at the emission spectrum, and we'll determine what elements are in the water. So TRIES, that we have an analytical lab here at the university. It's the Texas Research Institute for Environmental Studies, and it's an environmental research lab. And we do a lot of water sampling for the state of Texas. So they'll send us in the water, and we'll look for the trace elements of lead and arsenic and all those things that we want to track to make sure we have good, clean drinking water. Here's the distant galaxies, image the different wavelengths of light. So this is an infrared image all the way down to a UV light image. This is the composite, putting all these signals together. And so it's really cool. We can see lots of information about the stars and understand their chemistry. So this is the full electromagnetic radiation spectrum. Now, the words electro and magnetic mean something. So light is an oscillating electric field. And so if we're talking about the electric field being up and down, this would be a positive charge up here and a negative charge down here. So it's oscillating in time and through space, going positive charge, negative charge. So light interacts with charged things like electrons and nuclei and so on. And that's mostly the electric field. It also interacts with magnetic things. So there's a 90 degrees to that is a magnetic field. And how do we determine the ends of a magnetic field? North and south, right? So our Earth has a magnetic field around it. It's got a rotating iron core, a liquid iron core that produces a magnetic field for our planet. And if we have a magnetized needle, it'll point north. And so we know that's the north end of the needle and the south end of the needle. So we determine our magnetic poles, not in plus or minus like we do in charge, but in north and south. And so the light going through space will be positive electric charge and north magnetic field, and then sometime later negative charge and south magnetic field. And as it goes through space, it's doing this. So it's doing both at the same time. And it can interact with matter that way. If you have a charged particle and this oscillating electric field comes through and you're an electron on an atom, you might absorb some of that light, and so that's where the absorption spectrum comes from. If I'm an excited electron and I come to an atom and I bounce through all of the orbitals, I'm spitting out light as I relax, and so this electric charge can produce light. Now, it doesn't have to be an electron. It can be in an atom. It could be an electron on a wire. and I could push those electrons up and down on a wire, and it would emit light, and that's in the radio frequency range. So some of the things that we do with these different things like magnetic resonance imaging, that's the MRI scans we use, that's using radio waves. We've got microwave ovens in our house, that's using the microwave range of radiation. That also, for science, we use that for the rotation of molecules. So we can look at the sizes and shapes of molecules by rotating them in space using microwave radiation. Terahertz information. So when you go to the airport and they tell you to stand in the little tube and go like this, they're bouncing terahertz frequency light off your body. And it's we're not really doing spectroscopy with that. We're just imaging. But what it does is it bounces off of water. So you're just a big bag of water. So you stand there like this, and if it only bounces off of water or dense things, then it's not bouncing off your clothes. So that was the controversy, is that you just see a picture of your body without your clothing. You can see through your clothing. Yeah. And so so they have, there was some controversy. And so in order to implement that, they kind of have a little like pixelated thing of your face. So they can't like put a USB drive in and capture a bunch of images of naked bodies and then put them on the internet. Okay, people do that for themselves. They don't need the TSA doing that. And so you stand there and you get a screen. But now let's say you have a pistol or an explosive or something hidden under your clothing. It's going to absorb that light, so you'll see a dark shadow. Yeah. And so it bounces off of the water in your body. But if you've got something that is dense, like a explosive charge or the body of a gun or something like that, or maybe a big baton, a heavy duty baton that's down in your pants leg, they'll see it very easily. And so that way they can say, you go over here, beep, 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 Yes.
Would that also be, like, would it then also bounce off of, like medical grade, like implant?
Yeah, but it's going to bounce off your skin, your surface, wherever the water starts. Oh yeah, so it like a plate in your brain, or a head plate or something, or screws in your hip, of artificial hip. It's not going to even see that, which is great because we don't really care about that. Okay, now it wouldn't catch something that was kind of in your bum, because that would be inside. So, man, it's dedicated, I guess, but it's not gonna, not gonna catch that, right? Let's move on. Now we get to infrared light, and we have molecular vibrations. So this is the shaking of the molecule, and that is the molecular fingerprint. Okay, so this is really important. I know a lot of you are probably forensics chemistry majors, and so this is how we get the molecular vibrational fingerprint for a substance, and we can tell the difference between polymers and plastics and liquids and so on, even gases, all in the infrared. So infrared is very important scientifically.
How does that work? Like I have an infrared monocular.
Okay, that's a little different thing. Okay. Yeah. So it's looking at the infrared light that's being emitted by hot objects. So everything is a different temperature. And so you're able to get contrast in your image because everything's a different temperature. Yeah, that's how it works. But it's using infrared light.
Yeah, because if you don't have the actual flashlight infrared light part of it, then you're just kind of seeing it.
Oh, that's night vision. I thought you were talking about thermal.
Yeah, no, it's not thermal. It's,
yeah. Thermal is more passive infrared.
Right.
Yeah.
But yeah, I've played around with thermal. That's
yeah. Then molecular bonding and color changes is in the visible and UV. Okay. So this is where you're actually shaking the electron cloud. So the molecular vibrations, you're just shaking the bonds and angles of the bonds in the molecule, but you're not really doing anything with the electron cloud. You get higher frequency, and now the electrons are oscillating. So you're learning about the bonding in the molecule. And then you get to X-rays, you're looking at core electrons, and you can get atomic percentages of that. So you can hit something with an X-ray spectroscopy, and you learn how many hydrogen, nitrogen, oxygen, chlorine atoms are in there, because the core electrons are going to be different for each of those. Because the core electrons are very close to the nuclei. Every atom on the periodic table has a different number of protons. So if you can measure the core electrons, then you can measure how many protons are in the nucleus. Or you could go directly to the nucleus and use gamma ray. So nuclear transformations can also give you atomic percentages. There you're measuring the actual nucleus with gamma rays. And then the visible light, we have this mnemonic, Roy G. Biv. You ever heard that? Yeah, that's the order from red to blue. So red, orange, yellow, green, blue, indigo, and violet. Okay, so that's what Roy G. Biv is. Now, these are the equations related to spectroscopy. The book and Alex just show E here, but I put a delta in front because I want you to always remember that it's a difference in energy levels. So a spectral line is a difference between energy levels. So it's a delta E, really. It's not so much products and reactants. It's the molecule is going from a ground state to an excited state if it's absorption, or from an excited state down to a ground state if it's emission. But it's always this difference between energy levels. So I want to really emphasize that by putting a delta E here. And then it's H nu. The Alex uses F for frequency, which that does make sense, but traditionally it's given the Greek character nu. And so this also leads into one of my favorite jokes for you guys. When you're walking across campus now and someone says, "Hey, what's new?" You say C over lambda. And they'll say, "You've had DW." Yes. So C is the speed of light and lambda is the wavelength. But that's how you can remember that. What's new? Try again. What's new?
C over lambda.
Good. You'll never forget it. Okay. So here's Planck's constant. 6.66 times 10 to the minus 34 joules seconds. And then here's the speed of light. Again, this would be enough for your problems. 3 significant figures. 3 times 10 to the 8 meters per second. So light's really moving. 10 to the 8 meters per second. 10 to the minus 9 seconds is a nanosecond. Light's going so fast, it goes about a foot in a nanosecond. Okay. So it goes about 1 billion feet in a second. That's fast. Yeah. So, okay, it just was a picture from the OpenStax book showing you some of the things, the night vision and the infrared. Your gigahertz signals for your wireless data, that's down in this region of gigahertz, the AM radio, microwave oven, you've seen all that stuff. Okay, so now let's get into the Alex problems. So this is, again, just understanding and organizing spectroscopic terms. So you're asked to put the radiation in order, the highest to lowest, where 1 is the lowest. And so here we have radio waves and microwaves and green and red light. And we're just wanting to learn the order of frequency. So which of those is going to be the lowest frequency one? Radio waves. Yeah, so we're looking at that spectrum that was way down to the right. It was the longest wavelength, the lowest frequency. So there's our 1. That's the lowest frequency. And then what was next? Microwave was next, and then visible was over here. So then microwave was 2, and then red is the longest wavelength and lowest frequency and lowest energy light, a visible light. And so green is higher than that. So the red would be number 3 here, and the green would be 4, highest. So it'd be 1, 2, 3, 4. Now we just reversed that for wavelength because what's new? This is new, C over lambda. It's an inverse relationship. So the lowest radio frequency light would be the longest wavelength. Okay, so here the highest frequency light would be the shortest wavelength. So order of wavelength, green would be the shortest, then red light would be the next longest, then the green microwaves would be 3, and then radio waves would be the longest wavelength. So again, it's just sort of emphasizing this without you doing a lot of calculations, just so you know the trends. And then energy, again, H nu equals H nu. So if the frequency goes up, energy goes up. And so it's going to track with the first column, 1, 2, 3, 4 for energy. Okay. So this one ought to go fast when you're doing Alex. Okay, now let's do the calculations. So I like Alex problems because they're really wordy and they have lots of information in them. So this time about green plants absorbing sunlight for photosynthesis. Okay, and so it's got a wavelength, strongly absorbs at 642 nanometers. Okay, So it's absorbing red light. That's why it looks green. Okay. What's the frequency of this light? So we start out with 642 nanometer light. We want to go to frequency in terahertz. Okay. So we're going to get out of nanometers and into meters. So you're going to be using this one a lot. So get familiar with nano being 10 to the minus 9. So these are the same thing. So there's our wavelength in meters. And then we can use this, what's new, C over lambda. So we have the speed of light on top, and the meters cancel, and we're left with per second. Okay. So per second is the same thing as seconds to the minus 1, which is the same thing as a hertz, Hz.
But
So
C will always be, C is the constant.
yeah, C is a constant for speed of light. Yeah, that's right. And so that's 4.67 times 10 to the 14 hertz. Okay, but we want to convert that over to terahertz. And so a terahertz is 10 to the 12. So this is terahertz. And then 4.67 times 10 to the 2 will be 467. So that's 467 terahertz. So again, a lot of times we'll convert these over using the metric system. So you have gigahertz or terahertz or something like that. Yeah. Okay, let's do energy now. So this one, the trick on this one is that per mole. Okay, that's going to get you. Anytime you see the per mole, and you want to calculate the energy of a single photon, you got to get out of the per mole using Avogadro's number. And so we've got this situation where 614 kilojoules per mole, we want to get out of kilojoules, so 10 to the 3 joules per kilojoule, and then we're going to use Avogadro's number. And we're going to write it upside down. We're going to have this, we're going to essentially divide by Avogadro's number to cancel out that per mole. So this is the step that people don't get, and then they end up being off by 10 to the 23rd orders of or 23 orders of magnitude. So that's the energy of a single photon. That, you know, if I had a mole of those photons, it'd be 614 kilojoules. If I divide by Avogadro's number, that's the energy of one little photon of light at that wavelength. So we want to calculate the wavelength of this. So the wavelength is hc over delta E. You can see up here's the equation. If energy is h nu and nu is c over lambda, then energy is hc over lambda. And then I can just swap these two. I can bring lambda over to the left and put delta E in the denominator and end up with that equation. So here we have the Planck's constant, speed of light over the photon energy. And then I want to get out of meters and into nanometers. And so that's going to be 195 nanometers. And that is in the UV. So remember, the visible range was 400 to 700 nanometers. So 195 is much smaller wavelength, much higher energy. And that's why UV light is damaging to our skin. It can break carbon-carbon bonds. So when you're out in the sun, UV light, if we don't have the ozone layer protecting us from this really deep UV light, it comes through, hits our skin, starts to break apart carbon-carbon bonds. Now, you know, we're made to be in a radioactive environment. And so we have the property of our skin is that it produces dead skin cells constantly. And so we have a protein shield. So that light hits that protein and will break carbon-carbon bonds. But if you're out a lot, it'll penetrate through some of that dead skin and it'll burn the healthy, you know, live skin underneath and damage it. You get a burn from the UV light and you get a sunburn, and then it will kill those cells. And guess what? It peels off. Like, it produces more dead skin and protects you again. But that burn, you have to deal with the burn. Okay, now let's look at spectroscopy. So these are the spectral lines, like we saw in the Jesus spectrometer. Those lines on our eye and the photographic plate, we plot on the computer as peaks. And each of those spectral lines is a difference in energy levels. So you see this delta E piece. This delta E piece refers to these arrows, right? Those arrows are connecting two energy levels. So you have energy levels on the right and spectral lines on the left, and each one of those spectral lines is a difference between the energy level. So you can see that this one is for the A to C transition, this is the B to C transition, and this is the A to D transition. And I've got them color-coded for you so you can see the arrows. Now the up arrows mean we're absorbing light because we're going from a relaxed state to an excited state. And if I wanted to draw emission, the arrows would go down. I'd be going from an excited state down to a lower state, and it would be spitting light out. So you can kind of show this as light's coming in to the system like this and hitting the atom, ion, or molecule and causing it to absorb that photon of light and jump up here. Okay. And we still don't have a good theory. It's more for emission. We really don't have a good theory for what causes the molecule or atom or ion to emit light, like when it will happen for a particular ion. We can do statistics and we can say, yeah, it's proportional to the cube of the energy difference, but for a particular atom, we have no idea when or why it drops. In fact, the guy that invented quantum mechanics, that did the math, his name is Schrodinger, and he wrote a letter to his friend and said, I can't stand all this damn quantum jumping. He said, if we can't get rid of it, I'll be sorry I ever got involved. And to this day, we still haven't gotten rid of it. Meaning we haven't come up with a theory for what causes emission. Okay, we know how statistically it behaves, but we can't for a particular atom, ion, or molecule know when that atom is going to emit that light. So it's kind of an interesting enigma. So here's some questions that you'll have in ALEX related to this energy level diagram. What is the energy of the electron in the ground state? So A is the ground state. The lowest energy state is the ground state. So it's kind of like a building, only there's no basement. Right? The ground level is the lowest level, and that's what you have for these. There's only one ground state. There's lots of excited states. What's the energy of the electron in the first excited state? So there's lots of excited states. So these up here are excited states. So the first one is B. So the energy at B is 850 zeptajoules, ZJ. So these are, in the ALEX, you look at the little plot and you answer the questions. The arrows represent situations where energy is either absorbed or emitted. And so in this particular energy level diagram, which would you select? Because you have little bullets. Absorbed, yeah. So this is going up. Up arrows are absorbed. Down arrows are emitted. So ALEX may give you a down arrow, so then you pick emission. And then the fourth question we'll do on the next page. Okay. So what wavelength of light will produce the A to C transition? So that's asking for a spectral line. What wavelength of light would be detected? And so we got to take the energy difference, the delta E, and convert it to wavelength. So let's do that. So it's EC minus EA is delta E. So that's 1350 zeptajoules minus 500 zeptajoules. And we get 850 is the difference. That's just the first part of the problem. Now we got to convert that over to wavelength. So lambda equals HC over delta E. So we have Planck's constant. We've got the speed of light. And this 10 to the minus 21 is that lowercase z. So we can just take the z out and put in 10 to the minus 21. We don't have to do a whole conversion parenthesis thing. We can just, they're the same thing. So take out the z, put in 10 to the minus 21. Okay. And then we're going to end up calculating this in nanometers So it's 234 nanometers. Okay, so 234 nanometers. That's less than 400 nanometers. So if you had to classify this, this would be UV light. Okay, so I don't know if Alex is ever going to ask you that question, but that's what you need to know. You look at that and you say, yeah, it's less than 400. That's in the UV. UV light is really handy. A lot of things fluoresce in UV light. UV light is really hard to see, and so when something fluoresces, like you can turn the lights off and use a UV light. It's called an alternate light source. You can find pet urine that way. So you can go on Amazon and buy a UV flashlight for a couple of bucks, and then if you got a kind of a funky smell because your cat sprayed the curtains or something, you can find where to spray the Febreze. Okay, so you turn out all the lights at nighttime, walk around your house with the UV light, and you are a forensic scientist. You're looking for the evidence, and you find the bodily fluids from the darn cat, and spray something on there that's going to oxidize that urine, and the smell will go away. And so OxyClean, Febreze, I don't get any sponsorships, but these kinds of things that oxidize, you want to look for the, oxidize and kills odors. Doesn't just cover them up. It does actually break down the organic compounds that are causing the smell. So there you go. Free tip. Okay, so let's some other kind of Alex questions related to the energy level diagram. So looking at this, which is the ground state? Yeah, very good. Okay, so the ground state is A. So you put A in the box. How many excited states are there? There's 4 levels, but there's 3 excited states. So that's good. Put a 3 in the box. How many lines are in the absorption spectrum? Okay, this is the tricky one. It's every possible combination. Okay, so we got A to B, A to C, A to D. Those all started in A. What if we're in B? We've got B to C, B to D. And then what if we're in C? We can go C to D. And with these 4 levels, there are no other combinations. Okay. Now I've gone through and color coded them. The closest energy levels are the shortest energy difference. That's going to be the longest wavelength. That's going to be the reddest one. So I color coded them. I was so proud of myself on this. Okay. The next closest energy level is B to C, so it's orange. Roy G. Biv, right? Roy. C to D is a little further apart, so it's yellow. Okay. And then we start skipping levels. Well, A to C is shorter than B to D or A to D, right? So that's the G. And then B to D is pretty long, but it's not as long as A to D. So that's the blue, and then this is the violet. So isn't that cool? Anyway, I was so proud of myself making the colors. I was like, hey, I've got 6. I can do Roy G. Biv. I don't have the I, but I got the V for the violet. So there's 6 absorption lines in this spectrum. Pretty complicated spectrum. If you make it to CHEM and you're in my class, some of these will be not allowed by symmetry. Okay, but that's just a little foreshadowing. Okay, so which transition causes? Oh, I gave it away. The shortest wavelength is the longest arrow. Longest arrow is the largest delta E. Big energy, short wavelength. Okay, A to D. And so small energy, long wavelength. So A to B is the longest wavelength. And the color coding helps you with that, right? But also you look at the levels. A to D is the largest arrow you could draw. So that's going to be the shortest wavelength of light. Hopefully you like spectroscopy. It's what I teach every fall. So, and in graduate class too, occasionally. So I absolutely love it. This is CHEM. This is the fall semester of CHEM is spectroscopy and quantum mechanics. Okay. So here it is. I went ahead and put this into Excel and drew the spectrum. So I went in and I figured out, okay, of these energy differences, what would we see in the spectrum? So if we plotted these by wavelength, this is the color coding that you would get. You'd have a red peak at 2,000 nanometers, the orange peak, which is the B to C transition. You can see B to C. We come in at 1,400 nanometers. And then the next one, the C to D transition, would be here in the yellow at 1,000. Now, these don't really correspond to the colors in the visible spectrum. That would be 400 to 700 nanometers, but they're definitely in order of the colors. So Roy G. Biv here. The yellow would be the C to D transition. The green would be the skipping a level, going A to C, and then B to D, and then A to D. So this, if you're looking at the Cheez-It spectrometer, you're looking up at the spectrum there, you see all those different colors. That's what you're seeing right here on this in this spectrometer. So did everybody get to see this? You can come up and play with it afterwards. Did you get to see it? Okay, here. So I want you to go. Oh, wow. Yeah, see? That wasn't staged either. I could see like she was truly impressed. Okay. Okay, so your questions. I mean, we've covered the material for Monday. So it's just the lambda to nu to delta E calculations. Don't forget Avogadro's number. If you see the per mole in there, that's the thing that's going to mess you up. And then just working with energy level diagrams and the spectrum. Good luck. And then start on Wednesday as soon as you can.